Welcome to the session. Greeting of the day. In today's class, we are going to talk about the various mechanical tests available for the welded materials. In previous classes, we have discussed about the various welding processes, and in welding process, we have seen the various classifications of the gas welding, arc welding, resistance, solid state, chemical welding process, and radiant energy of electron beam and laser beam welding process. In all these welding processes, after welding, whether it is having the discontinuity of defects or it is not having the defects, we need a defect-free component. For that, we have to go for the inspection. On the inspections, I am classifying into destructive tests and non-destructive tests. In the destructive test, again I am classifying into two categories of quantitative test, and then I am dividing in the second categories of qualitative tests. In the quantitative test, which contains having the unit, the important point we should note here, the quantitative test having the units. What are they? I am dividing this quantitative test into three categories of 1, 2 and 3 as tensile test, toughness testings and the hardness testing process. This tensile test we are going to measure in the megapascals, which having the units. Toughness test we are going to measure in the joules, which have the units. And hardness test, Wicker hardness HV we are going to measure. Those having the units I am measuring in terms of quantitative tests. And when I am coming to the second categories of a qualitative test, which does not have units, it is having no units, but we are measuring the quality of the weld through the various methods of macro testings and the bend testings. Bending, we are disturbing the specimen, it is going to break, but how many angles it is break, it is not a unit. How many angles it is 90 degree it is bended, or it is 45 degrees bended, how it is capable ductile material, it is bending there. After bending, we should check the bended location. In such a way, we can able to identify the quality of the weld by seeing. So, bend test and fillet weld fracture testings and butt weld nick break test. This four comes under the qualitative testing process and the quantitative testing process, which having the total number of tensile, toughness and hardness. This image represents the various destructive specimens. These destructive specimens you can able to see. Here I have mentioned a tensile specimen components, which I have this one. Okay. And see here the rod has been braked for destructive to test about the tensile material property, materials tensile property. And some other fractured fillet welds also I have braked, showing the braked zones where we have to find the failure is there or not. So similar patterns of various specimen. Here I have given about impact specimens. Here this one, you can see the impact specimens, how it is braked to identify the failures. So before going to the various testing process, we should understand the first definitions of the properties. So mechanical, describe about the action of force and the motions that we know. And then about the property, something that makes one material useful for those jobs. This includes the property of, what are the properties are there available? We have hardness, toughness, tensile and the ductility. I am defining this properties hardness as the ability of the material to resist the indentations, and then toughness I am defining as the ability of the material to absorb impact energy. Yes. And then the tensile strength, we know this, the ability of the resist to act of a pulling forces, how far it is resisting. So ductile material, we know this, ability of the deformation plastically under the tension, how far it is deformed, how far it is elongated with respect to the tensile load. So that is how. So we have done the welding process in this way. We have taken two specimens and we have welded. We have welded there in such a way. We have taken the V-groove joints and we have welded there. So this is the welding. So this is the welding process we have made. I want to cut the specimens where I want to do the specimen test, where I want to, instead I want to do the tensile, I want to do the toughness, I want to do the hardness test, I want to do the macros. So these things are to be done in the welded specimen. How we have to cut? I am making the cutting sections in this format. So this locations I am getting, this is the weld zone. This is the weld zone I am cutting. So this is the total piece which represents in the yellow color. And I am cutting those things in this part I am taking. And I am showing you now. You see, this is the part I have taken. This is the weld zone. This is the weld region where it is at the center. And on the weld specimen, I am cross section, I am cutting this every part. And I am indicating there. See, this part at the outermost left end I am using for tensile test. It means the cross section perpendicular to the weld. Weld we have done in this part. And then the specimen has been cut perpendicular to make the tensile test. So this is about the tensile test 1. And the second specimen I have taken for the impact test. Tensile and impact. Then you see, and next specimen we can able to use for hardness test. Maybe and also for macro testing process, macro inspection for quality welds. And the last time again using for the bend specimen. Here we have to see weld has been in this location. Weld is available here. You see, weld is available here. This is the thickness. So this zone is the thickness. This zone is the thickness. You see, this zone is the thickness where it is available. So we have to cut as like a different parts, and this part are subjected to the testings. This testing process we have already known by the MOS. So those things we have to understand. Now we enter into the number 1 of a tensile test, how it is classified. As I told earlier, this is the specimen we have taken. See, this is a workpiece available as in our hands. So as in our hands, I have taken a cutting of this zone. I have taken the cutting of this zone. I have made the cross-sectional cut, and I found that the perpendicular zone, the specimen has been taken for tensile test, which is perpendicular to the weld zone. Weld has been in this direction. I am taking the specimen to cut in this direction. So that is how I have prepared for the plate. In case of pipe, how we can do? In case of pipe, you see, we have a thickness of straight thickness we need. Whatever it is, a pipe may be a circular format, but we need a flat specimen. So in this location, we are getting a flat. So this flat I am removing. This is the flat. So here also similarly, I can able to create a small flat scale. Here also I can able to make one small flat scale. So these flat scales are taken out and it can be utilized for testing purposes. And this flat scale can be taken where it should be welded. Non-welded specimen tensile test for base material. And the welded zone we can take for tensile test for welded zone. So such cases we can able to do. So this are available. This when we are cutting here, the weld is happening. This zone will come. When we are cutting here and this zone straight path we are taking, we can able to take about the weld zone tensile test properties. In case if the thickness is very large, by the ASTM standards, the fixed quantity of height of 25 mm we can utilize for testing purposes. There the subdivision standards are there that we have to use there. So in case of large thickness, we should cover tensile test of heat input may vary in the surfaces, may vary in the bottom, may vary at the centers. Therefore, I have to plan accordingly to cover all the zones. I am covering the specimen of the center part, this part I am taking, and I am taking the next second part, this part I am taking, and also I am taking this part also I am taking. So bottom, center and the top. I have sliced from the welded zones and I am going to weld here. You see, this belongs to the top one, this belongs to the top one, and this belongs to the center one, and this belongs to the third one. So likewise we can able to create the large thickness specimens. So this is for our identification that the weld has been taken place here, weld has been taken place here, and the cutting perpendicular to the specimen. Here in case for all weld specimens, all weld means the entire specimen itself taken in the all weld zone. Here itself we have taken, not at all this base material has been taken, all weld specimen has been taken for testing, get the information about whether the weld quality is good. You see, a section of weld is cut or mechanical cut out across the test pieces, testing the tension failures. Here it is generally Newton per mm square or megapascal we can able to take. So this is the perpendicular to the weld, and this is a tensile test of elongation we are doing. So these are the various terminologies how we have to take the tensile test. This is the reduced sections, and heat affected zone is here. You see, this is the heat affected zone, should cover both sides. This is a weld center. So this is the weld center where we are in the reduced cross sections, and this is the grip of the same specimen. Here the weld, I think we understand this. Here the weld is there. We have taken in this way. So weld is available here. So weld is there now. At center it is going. So we have taken the V grooves. At the center the weld is going. So I have cutted here. You see, I have cutted in these locations. It may be at the through thickness also. Through the welding has been done in the path, and I have taken the specimen itself in this path itself. It means all weld zone, all weld material I have cutted for testing purposes. So this is the example. Initially the gauge length is 50 mm. First before tensile test 2 marks are made at 50 mm apart. So total this is the gauge length we have taken. So total, and then now after testing it has been ductility elongated from 50 to 75. It has been elongated, and there it is a crack has been formed. So that measurement 50 to 75 we can tell elongation is the elongation 50% has been taken place. If it is 100 it will be changed. So that is how we can able to understand. So this is about the tensile test. When I am coming to the toughness test, next one you see, these are all destructive test which contain the units. Here we have Newton per mm square as a unit. So it may be a transverse weld or the all weld method. So these 2 points are important. Now we have told this transverse weld is nothing but a perpendicular. So when we are taking the specimen in the perpendicular way, so likewise this is a transverse weld. This is number 1 condition. When we are taking in the all weld specimen, this is a all weld specimen. You see, all weld specimen, all weld tensile test. This is case number 2. Tensile can be taken in the 2 conditions: transverse weld, all weld specimens. So now we are coming into next one of toughness. The object is measuring impact strength at different weld areas. It should observe the impact and withstand how far it is withstanding. So that is also will break. There the elongation, here the absorptions. Information supplied for testing material type, we have to give notch, how much notch specimen, how much we are taking. That should be give specimen sizes 55 into the field C. Test temperature, at what temperature, room temperature we are doing the testing process, or as the cryogenic temperatures, at what temperature the test is performed. Notch locations, impact strength values. So those things we have to give. So see, we have taken the specimen. This we know we have done the welding process, and weld is here. The weld is has been done here. And the first specimen, this first specimen we have taken for tensile. I am taking the second specimen now, maybe here, for impact test. So again the third one we have to take for hardness macro. So such things can be taken. Now I have taken this part. So how much dimension to be there? This one, this dimension I am telling, is the total length occupies of 55 mm. Of 55 mm. It means this side and that side together, welded to be at the center. This here we should have the weld. Here we should have the weld. Here it is welded. Here it is a welded. So likewise we have done. After that, how much width and the thickness and height to be there? It's both are 10 mm. You see, this is 10 mm and width also 10 mm. The length about 55. Inside depth and this one. See, this one is a 10 and this also 10 mm we have taken. Where we have to going to break opposite side. The pendulum we have to go into straight to the specimen. First we have taken the 45 degree and depth of 2 mm inclined. We have taken 45 degrees. V-notch, 45 degree V-notch has been taken, and then this is 55, 10 out of 10. This is a ASTM standard E23. With respect to this, we have to go for toughness testing process. So this is the setup of impact testing. We have to keep the after preparation from the welded specimen. This is the welded specimen. After taking, we have to keep it here, and pendulum will strike. Where it will strike, it has to strike a opposite side. See, opposite side of the notch preparation. It has to weld. It has to create the notch opposite side. V-notch has been created this side. Heating happens the opposite side of the V-notch. We have holded, and we are getting the impact load has been, sudden impact load has been given. How far it is observed in terms of joules we are going to report. So here also, as usual, we have, if in case of large thickness available, we should take at the top, at the center and at the bottom. How far? The heat input is varying. At the top is varying, center is varying, and the center is also varying. Therefore, we are taking the 3 locations with respect to locations also. Here the location is at weld center. Right. And then here and this one here at, we can tell here at point of heat affected zone. Here it is weld. Here it is heat affected zone. And the third one I am taking, this one at the base material. See how far I am comparing. I want to compare with the base material. Base material has been fabricated, casted with one property. And even after welding, the welding should match the base material property. Then only it is good. If the property is reducing, how it will withstand the desired one? Not possible. Therefore, this base material property, base material toughness should match with the weld toughness. So that is how we are, therefore we are comparing those results. 3 locations we have taken and comparing. The average can be taken. So I want to analyze these destructive testing methods. In case after breaking, this 55 mm specimen has been taken. This is a 10. We know this. This is 110 and height 10 and 10 we have taken, and a length of total length of 55 we have taken, keeping the weld at the center, and we have applied the impact load and it is braked. After braking, by visualizing those specimens, we can tell whether it is belong to the ductile mode or brittle mode. In case if these specimens are looking visually in this format of texture, in this textures we can tell it is 100% ductile. Because it is elongated, it is occupying. We are getting little bit cup and cone here, little bit cup and cone forward we are getting. So that is why I'm referring this as a ductile in nature. The material having some ductile property we are identifying. But here you see it is totally flat. This zone is totally flat, as it is like a biscuits or a glass, it is breaking. So that is why I can able to refer this material as a 100% brittle. By visualizing the texture after breaking the specimens, and we can able to identify whether it is belong to brittle or ductile. Where we are measuring, it specifically will fall in the V. This is the V we have created. This is the V piece we have created, and we have done the impact load here, and we have holded there. We know this is the same location we have made. We have done holded there here. Right? So we have kept like this, and the breaking point has been occurred here. And when we are breaking, this point we are measuring. See, point I am measuring. This point belongs to this location. So how far it is breaked, whether it is brittle or it is a ductile. So next they having the classifications of a Charpy test, and then Charpy and ISER and CTOD test also. These are some of the classifications of toughness testing process. Or if we have to take 10 into 10 specimens for both all Charpy and ISER tests. So I want to compare these two categories. For example, I have done the impact tests. I have done the impact test at one is done at a room temperature, one is done at a minus 20 degrees centigrade. For example, we are going to measure the impact load. Load has been given, and then at an average of room temperature we are getting around 195 for steel. So therefore it's an average of 195 joules we are getting. But similarly, the same material when we subject it to the minus cryogenic temperature at very cool condition, what happens? The impact is breaking, it is converted to brittle. Here it is act as a ductile material, therefore it withstands more property. At 194 joules impact energy we are getting. But the same material when it is subjected at the temperature of cryogenic temperature of minus 20, it is totally converted to ductile to brittle fracture. It is totally break, texture is flat. Here the texture is little bit cup and cone we are getting. Cup and cone we are getting here. Little bit it is a 49, 53, 49, average is 51. So compare, here it is a 200 and it is a 50. It is reducing. So this is we name as a ductile to brittle transactions. So now we have completed tensile, we have completed toughness, and we are going to hardness now. In this hardness we have three categories of brittle, Vickers and Rockwell. I am naming this as a brittle B, Vickers or Rockwell. We will see now. So what is this? To measure resistance of the material against the indentation. We have studied this already. So measurement of resistance of material subjected to the indentation load applied on the surface. So what happens? So here also inspections of material type, location where we want to do testings, those information we have to give. So this is the specimen I have taken. This is the welded one. You can able to identify, and I am showing the cross-section view of the specimen. I want to take at three locations as like in the impact, as like in the tensile. Here also I am taking where this point we have taken at weld metal. Number 1 I have taken. And number 2, nearby to this there is a fusion boundary layer. So here also we should take what is the change after, because high heat input causes a different hardness and less heat input causes a different hardness. You see, we are going to weld here and more heat will be subjected at this center point, and this heat will be distributed around through the material. But when it is distributing, that all heat will not be distributed. Heat going to reduce by the conductions. Therefore, and when it is coming to the end point, here it is not even heat is not subjected. Here it is 100% subjected. Here it is 90%, 80%, 60, 40, 50, 30 and 0. Heat is not even subjected. That we call it as a base material. So that one weld method. Then the fusion boundary, and I am naming this zone as a third one. This zone as heat affected zone. Here also we should do the indentation, and at the last this one as a fourth one as a base material we have to check this testing process, and also with respect to top layer, center layer, bottom layer. So indentation we have to do everywhere. So multiple readings we will get accordingly, then we should average those things. So this is how the hardness survey we have to take. We have here the three types of informations we are getting. So we may get, generally we use a diamond or steel ball for the indentation. You see, here I am using maybe the ball indentation. Through the ball we can able to make the indentation, punching penetration we can do on the surfaces. Otherwise we can use the diamond indenter. The shape of the indentation may be ball or maybe the diamond, whatever it is. So this is ball. I am having the ball indentation to punch. Otherwise this is the diamond indentation where we can able to punch. Accordingly, the different cases can be formed there. So I am naming how far we are using. For our understanding, we know there are different types of hardness tests are there, such as Vickers hardness test, Brunel hardness test, Rockwell hardness test. I am identifying this Vickers diamond indentation will be contain use of diamond indenter. The name itself says Vickers diamond indentation process. It uses the diamond indentation. Diamond indentation. And then this Brunel hardness test contains the B of using the steel ball. Always uses the steel ball. So here the Brunel ball using, the diamond using, and Rockwell, the R represents, we can understand this either or, maybe ball indentation or is the diamond indentation we can use. So for Vickers diamond, we are using the diamond. For the Brunel B, we are using the ball. And for Rockwell R, either or we are using the ball or diamond for our hardness test. So likewise we understand. So the setup we can apply from the load, how far whether we are giving the 1 kg or 2 kg or how much the load applied, according to it will make on indentation. This indentation we are talking. This indentation may be the ball indentation or otherwise the diamond indentation on the surface. So see here I am applying the diameter of the ball is 10 mm and 30 kilonewton of load is applied over the ball, over the specimen, and the indentation has been found. The indenter is steel indenter, steel ball. So Rockwell ball, Rockwell C, a cone shaped indentation. Rockwell I told R. This R represents either R ball indenter or otherwise the diamond indenter. Therefore, Rockwell B scale, Rockwell C scale is there. So in the Rockwell B scale, ball indenter is used and the load applied. And the Rockwell C scale, cone indenter. Cone is nothing but a diamond cone applied there and some load is applied. So for Rockwell C scale, when we are using with respect to dependence on the indentation, the scale we are varying. When we are using the ball indentation, B scale we are referring. When we are using the cone indenter or diamond indentation, we are using the C scale or for either or. So that is how we should take for hardness testing. At the top surfaces we are taking at all locations. See, this one weld zone, heat affected zone, and the base material. So because we are having here the values of some 240 HV the unit, and Rockwell harness RC 22, and Brunel the unit is BHN, Brunel hardness number. This is HV hardness Vickers. This is Rockwell harness C scale, and this is Brunel harness number. So likewise we can able to understand the various types of hardness test. So as of now we have seen these three. Now you see macro testing process, bending fillet we have to see. Macro testing, it is nothing but a quality weld. How far it is? The magnification will be less than 10 times. The magnification will be less than 10 times of x. We are seeing a naked eye, it is about 1x. I am magnifying the same viewpoint to 10 times the lenses. So magnification is less than 10x we consider as a macro. If greater than 10, maybe I am magnifying up to 50x, magnifying up to 100 times, 200 times, I am naming this as a microstructure. Microstructure. In the macrostructure only we are going to find the defects, macro inspections. So these are the various inspections we can able to find there. So visually we know what are the defects are caused. In that cross section, through the macro, little bit less than 10 times of zooming, we can able to identify. See, so excess weld metal height. Here it is weld metal height is increasing. We are identifying the defects here. We are identifying the defects. How far it is done. Lack of sidewall fusion, lack of root fusion. See, and then slag inclusions also are there, both lack of sidewall slag inclusions, root penetration. Here the root penetration is not occurred extra. Additionally, root penetration is done here. And then porosities, laminar tearings, and the pore here 90 degrees, smoothly to be blended. I have already told you this. So these various defects can be found by using the macro inspections. So such things. These are all defects to be avoided. Cases, causes and remedies are there to avoid this defects. That is different. First, but we should identify. This is identifying method. Destructive test, first we should cut and we are seeing this. This is over. So the bend test. So this bend, even though it is a destructive, it is where only we are identifying the angle, how far it is bended. So here I have taken the specimen. You see, this specimen has been taken and the load is applied over there. How far it will bend? It will bend like this. It will bend like this. Therefore, this is the root side. We know. This is the face side. Here we have welded. Here we have welded. This point we have welded. What happens if I am bending through this part? The root will also have more tension and it will bend. If the root is not properly welded, it will have a break. Then we find that defect is there through the destructive method of bending action. If the standards, if it is bended greater than 90 degree, we understand even though it is defect is there, it is negligible. Even if it is not even possible to bend, it is at a little bit when bending process itself it is breaking, then we identify it is not sufficiently withstanding the strength factors. So how far we can do this? So this is the original specimen. You see, the impact load is given on the specimen and it should bend in such a format. So after the bending action, I have taken the remove the specimen. Specimen is removed and the weld is available here. The weld is available at this spot. So here it is available there. So it should withstand the bending actions. Tensile, bending, hardness, toughness. These are the various mechanical designing properties, mechanical property designing tests. I can able to do this test in the various format. Maybe I am keeping the bending action has been done here. This is root bend. The root operation, this is root we know. Which is one is root we know, this is root. So this is root. We are going to weld here. We have done the welding. Here, this is root. Right? This is root and this is the face. So the bending action can be done root to elongate, so that is for root bending operations. And similarly I am applying the same load here, but you see it is reversed. Face is on bending, this is a face. So face is on bending. Here the root is on bending, here the face is on bending. Maybe I can able to do the side bending also. Both will bend. So the side bending, so the weld is done here. At this point we have it. The weld is here like this. Like this it is there. Side bending. We have taken the specimen and the side cross section until this is the specimen. This is the root. We have pressurized here. Face is under tension. And I reversed. Here it is weld or faces. I am doing the pressure here. Root is under tension. And here this is the sides. Now I am doing the pressure here. Side is under tensions. So this is called as a side bending process. So this likewise we can able to do. You see, here I am doing. This is the V, root bend. So this is the face available. This is after bending, face is going to elongate. Here similarly side is going to elongate. So these are the various categories where we can able to find the defects through destructive methods. So this is also done fillet weld, but welds. So fillet in case now all these things we have seen about to butt welding process. But now we are going to see about the fillet weld also. This is fillet weld. We have to hit a break here. When it is hit, what happens? It will make the breaking in such a way. So when it will break here. When we are making a hitting process, it will break here. So in that cut, the surface are there. Two surfaces. One this surface and this surface. Those surface we have to check. So it will break like this. When I am hitting here, it will break like this. So this is called as a fracture like saw cut. As it is like a saw cutting process, it have a fracture. So that is called as a fracture of like a saw cut. So I am referring, after breaking I have to see here. We are breaking the specimen to check whether it withstands those load. Therefore after breaking I am opening, I am seeing. So these are visually inspected for, see, after when we are breaking you can see lack of penetrations occurred even though it is visually welded. Physically it is welded, looks well good. But after breaking we can see inside part it is a lack of penetration is there, lack of mortar metal is not filled, unfilled groove. So such defects will be available inside. So such things we have to cut and verify. So this is about butt nick break tests. So now we have done two welds, top weld and bottom for the large thickness. Similarly, I am also want to cut here and I want to inspect this surface. This is the total specimen. I have cutted and opened and seeing those fairing surfaces, welding zones. So this surface I am seeing and I am seeing these surfaces. So in the surfaces this is visible. So this surface is represented here. This surface is represented here. This is looking inside surface. On the surface as like this content, here also some defects are available. See, lack of slag inclusions are there, maybe tungsten inclusions or laminar tearings, some other inclusions and defects are available. So this is how we can able to identify the various testing process. So likewise, see, here we are making the cutting treatments and we are checking defects are available. So I would like to summarize these things you see here. We test welds to establish a minimum level of mechanical properties. Yes, and then we divided the test as a qualitative test number 1 and quantitative test as number 2. In the qualitative test, what we have seen in quality, like we measure first we have a unit. This having the unit in quantitative, the terminology quantitative represents the unit. Here we have seen about the hardness test. This hardness contains wicker hardness, brittle hardness, diamond and rockwool hardness also there. So those we have seen, and later we have seen the toughness, impact toughness, Charpy and ISO tests, and then the strength factors, the tensile load, how we are applying. On the same, the ductility also we can able to check. This all contains unit. You see Newton per mm square, joules, brittle hardness number, so elongations, percentages. So we have units there. So that is why I am named as a quantitative methods. On the other hand, we have qualitative methods through we are not having units, but visually after breaking you can able to see the defects. That is how the macro test, which is less than 10x we have done, and the bend test we have done the angle and find how far it is bended, and then the fillet weld fractures, but these all belong to butt welds and fillet welds. So L joint and we have hit it, fillet weld has been breaked and surface we are viewing for lack of penetrations. So fillet weld and butt nick break the tests. The remaining part of the subjects we'll see you in the next session. Thank you.